All right, let's just jump right in. Welcome to today's explainer, 8th graders. I am super excited because we're about to look at shapes, math, and honestly, maybe even your own personal choices in a totally different way. Today, we're actually bridging the gap between rigorous, hard, and fast mathematical geometry and some incredibly powerful life principles. We're going to see how the absolute exactness of math can teach us something super profound about how we live, how we think, and how we grow. So, get ready to stretch your minds a bit, both mathematically and personally.
So I want you to really think about something for a second. What on earth do architectural blueprints, geometric triangles, and your own mind actually have in common? I mean, at first glance, there's no way they're related, right? One is for building houses, one is a math concept on a chalkboard, and one is, well, it's you. But there's a hidden thread linking all three, and it all boils down to structure, consistency, and transformation. Think about it. If a blueprint isn't consistent, the whole building falls apart. If a triangle's structure isn't consistent, the math totally fails. And if our minds aren't consistent, well, we're going to find out exactly what happens.
Okay, so to really get this, we've got to nail down the math first. Let's talk about the definition of geometric similarity. In the world of geometry, two figures are considered similar only if they have the exact same shape. But listen, we don't just eyeball it and say, yeah, it looks close enough. Mathematical similarity has strict, unbreakable rules. The figures absolutely must have perfectly congruent corresponding angles, and their side lengths must be perfectly proportional. And just as a quick reminder, congruent just means exactly equal in measure. If even one of those conditions isn't met, then mathematically speaking, the shapes are completely different.
Now, here's where it gets kind of tricky, because we toss the word similar around in everyday life all the time, don't we? Like you might say, oh, my new shoes are similar to yours, which just means they look vaguely alike or share a vibe. But mathematical similarity? It does not care about vaguely alike. No way. It demands exactness. We're talking proportional sides and congruent angles. And why is that absolutely crucial? Because when architects are drafting blueprints or geographers are plotting maps, knowing that figures are perfectly mathematically similar stops disastrous errors from happening. In the real world, exactness builds trust.
And that brings us to the real engine behind all this, dilation. Dilation is a transformation that simply resizes a shape. It can blow a figure up to make it huge or shrink it down, creating a newly sized but perfectly similar figure. And it does this without ever changing the shape's fundamental structure. Think of it exactly like pinching the screen on your phone to zoom in or zoom out on a photo. The image gets bigger or smaller, but your friend's face doesn't suddenly stretch out and get distorted, right? Dilation guarantees that the internal truth of the shape, those angles and side ratios, stays completely, perfectly intact.
So how do we actually prove that a shape was dilated properly and is truly mathematically similar? Well, you've got to use this super practical two-step test. Step 1, check if all corresponding angles are congruent. Every single angle has to match its partner perfectly. Step 2, check if all side lengths are proportional. Basically, did they all multiply or divide by the exact same scale factor? If both of those steps check out, boom, congratulations, you've proven geometric similarity. But if even one single angle is off, or just one side didn't scale correctly, the whole thing fails the test.
Let's make this super concrete with an example. Imagine you've got an original triangle plotted out on a graph. The points are at coordinates 1, 1, 2, 2, and 3, 1. Now, if we apply a dilation with the scale factor of 2, we literally just multiply every single coordinate by 2. That's it. So our new, bigger triangle sits at 2, 2, 4, 4, and 6, 2. Because we applied that exact same scale factor of 2 to every single point, the side lengths stay perfectly proportional and the angles haven't shifted a single degree. We have totally maintained mathematical similarity.
And here's something that beautifully shows just how rock solid this rule is. What if we throw a curveball and add rotation into the mix? Imagine taking that newly dilated triangle we just made, and you just spin it. You rotate it 90 degrees or 180 degrees around the graph. Is it still similar to the original? Absolutely. Spinning a shape does not change its internal structure. The angles are still congruent, the side ratios are completely untouched. You can resize it, you can flip it upside down, but its fundamental truth is still mathematically similar to the original shape.
But hey, you really gotta watch out because appearances can completely trick you. Take a square and a rectangle, for instance. They both feature perfect 90-degree corners across the board, so they actually pass step 1 of our test with flying colors. But they fail step 2 completely. A square has all equal side lengths, but a rectangle obviously has different side lengths. Because those side lengths are not proportional to each other, they are not mathematically similar. So even though they look like they're in the same family of boxy shapes,
Structurally, they completely failed the test.
Okay, time to actually put your learning to the test. Let's look at a homework challenge straight from your assignments. Are triangles with side lengths of 3, 4, and 5, and a second triangle with sides of 6, 8, and 10 mathematically similar? Think back to our two-step rule. Look closely at the sides. How do you get from 3 to 6? You multiply by 2. From 4 to 8, multiply by 2. From 5 to 10, yep, multiply by 2. The side lengths are perfectly proportional because they share a totally consistent scale factor of 2. So the answer is a resounding yes, they are mathematically similar.
All right, let's tackle one more. Homework challenge number 2. If you apply a dilation with a scale factor of 2 to a triangle sitting at the coordinates 2, 1, 4, 2, and 3, 3, is the new triangle similar? I want you to try to mentally verify this. If we multiply every single number by 2, what do we get? We get 4, 2, 8, 4, and 6, 6. Because we applied that single rock-solid mathematical action, dilation by a set scale factor, across the whole shape without tweaking anything else, the structural integrity holds strong. That new triangle is 100% mathematically similar to the original.
Now here is where things get really fascinating. We're stepping beyond the math for a second to see how this builds into something huge. The curriculum we're looking at today links these strict geometric rules to a very famous passage, Romans 12:2. It says, "Do not conform to the pattern of this world, but be transformed by the renewing of your mind." Think about it. In geometry, a shape transforms by following strict, consistent rules to keep its internal truth. This text is basically challenging us to do the exact same thing with our own minds, to actively transform and renew ourselves from the inside out rather than just passively conforming to whatever random shape the world throws at us.
It is crazy how perfectly these two concepts map onto each other. In geometric transformation, we change the size of a shape through dilation, all while fiercely maintaining its structural consistency, those proportional sides and angles we talked about. And in spiritual transformation, according to this material, we renew our minds to maintain true moral consistency as we grow and change through life. In math, when a shape's internal values stay consistent, it passes the test. In life, when our internal values and our character are consistent, we become solid, trustworthy people.
And this whole idea right here, it's literally the cornerstone of the HeroesMart Academy Godly Learners series. The philosophy they present is that education absolutely must intertwine with biblical morality, because being educated without a moral compass can actually cause a lot of harm. I mean, think about it. What's the point of being highly intelligent and super educated if you just use that brainpower to keep making terrible choices that hurt you or the people around you? Intelligence on its own is just a tool, kind of like scaling a blueprint. But without the right moral structure, the house you try to build with that intelligence is just going to collapse.
And you might be asking, okay, so what's the payoff for me? Well, there is a real, tangible benefit to maintaining the structural integrity of your character. The curriculum highlights Romans 8, 6, 7, which promises a deep, lasting peace of mind to everyone who keeps their mind spiritually renewed. It makes sense, right? When your thoughts, your actions, and your values align perfectly, just like those congruent angles and perfectly proportional sides, all that internal friction just stops. You actually experience peace because you aren't living a distorted, out-of-proportion life.
So, 8th graders, as we wrap up this explainer, I've got one final, huge question for you to chew on. When you sit down to do your geometry homework, you meticulously check for exactness, truth, and consistency to make sure you solve the problem right. But as you grow up and navigate the messy challenges of daily life, are you going to demand that same exact level of truth and consistency from yourself? Are you willing to transform your mind with the exact same precision as a mathematically perfect dilation? According to what we learned today, the entire blueprint of your life depends on it. Thanks so much for learning with me today, and I'll catch you on the next explainer.